All right, the next thing that I want to talk about is what are called convergent sequences. So we say that a sequence, a sub n, converges to some number L. So it converges to L if the limit of a sub n as n goes to infinity is equal to L. Okay, so converges just means that as you take the limit as n goes to infinity, you get some finite number L. Here, L is a finite number, so we don't say it converges to infinity. Okay, if this limit's infinity, we say it diverges. So a sequence a sub n diverges if the limit of a sub n is equal to infinity or negative infinity, or if it doesn't exist. Okay, and then if the sequence has a limit and the limit's 5, then we say that the sequence converges to 5. So in general, we say the sequence converges to L if that limit is L. Now, there's a few things that I want to point out here. Let's just start very easily. The first is, if I look at the limit as n goes to infinity of 1 over n, and I think of larger and larger and larger values of n, it should be pretty clear that this is going to go to 0. I'll talk about the precise limit. Instead of epsilon deltas, because we're going to infinity, we have epsilon n limit definition of a sequence, but we'll talk about that. But if I look at the sequence 1 over n, it's clear that the terms get smaller and smaller and go to 0. So this converges to 0. Likewise, if I look at the limit as n goes to infinity of negative 1 over n to the n, okay, that's still going to be 0. And there's a nice way to see this. In one way is to just notice that the absolute value function is a continuous function. It's not differentiable at the origin, but that doesn't matter. It's a continuous function. And so I'm going to call this a proposition. Proposition is kind of a theorem, like a lesser important theorem. And so if you have a sequence a sub n, and the absolute value of the sequence goes to 0, then that means that the sequence must go to 0. Okay, then the sequence goes to 0, and vice versa. Of course, the other way should be pretty clear. If a sequence is going to 0, then taking absolute values just makes it go to the absolute value of 0. And if you want to talk about kind of a mini proof here, the fact that the absolute value is continuous means that you can move it in and out of the limit. And so the limit as n goes to infinity of the absolute value of a sub n is just the absolute value of the limit of a sub n as n goes to infinity. And so if one of them is 0, so is the other. And then we use the basic fact that if you have the absolute value of a number being 0, the only way that can happen is if the number itself is 0. So I guess there's one small step here. If the absolute value of x is 0, that forces x to be 0. There's no other number whose absolute value is 0, which should be pretty obvious in retrospect. So this is a very useful fact, and it can be applied in the above situation, because if you look at the limit of the absolute value of negative 1 to the n over n, that's just, if you take the absolute value, that just knocks off the power of negative 1 in the numerator, and this is going to become the limit as n goes to infinity of 1 over n, which we just said goes to 0. And therefore, since the limit of the absolute values goes to 0, so does the original. Okay, and so that's convergent sequences. If I look at the limit of, say, n squared, this is, of course, going to be positive infinity. So the sequence n squared, as n goes from 0 to infinity, diverges. And sometimes, because there's a few multiple ways that a sequence can diverge, because if the limit's infinity or negative infinity, or if the limit doesn't exist at all, sometimes it's customary to add that this diverges to infinity. And what that means is that it kind of tells you that the problem isn't that the limit doesn't exist, it's that the limit's infinity. So that's that. Now there's one thing that I think is important to talk about, and that's the relationship of the limit of a sequence to the limit of a function. And so before I get to that, let's actually just, for once and for all, deal with the limit definition of the epsilon definition of this limit. We say that the limit of a sub n as n goes to infinity is equal to L if, so this is a definition, if for all epsilon there exists a capital N so that the absolute value of a sub n minus L is less than epsilon whenever little n is greater than or equal to big N. Okay, so that's the limit definition here. And so the idea is it's very similar to the limit definition when we're talking about functions. If you want to say that this limit is eventually going to settle at L, what that means is that you can get arbitrarily close to that number L, and there's got to be some cutoff where you always stay within epsilon units of L. Okay, so it can't be that the function oscillates here. That's when the limit doesn't exist. So this, to say that the limit exists and equals to L, means that eventually all the values in the sequence get arbitrarily close to L. I'm going to get my bad drawing out of here now. Okay. Now, I think it's worth talking about the difference between the limit of a sequence and the limit of a function. And the example that I always like to think of is if you were to talk about the limit as x goes to infinity. We use x when we're trying to talk about real numbers and n when we're talking about integers. Okay, so x gets used for real numbers, n for integers. But the limit of sine of pi x does not exist. Because if you were to graph sine of pi x, think about what's going to happen. This will be 0 at 0, 1, 2, and so you get this function here, so 0, 1, 2, and so on, and it's never going to settle down. However, if you look at the limit as n goes to infinity of sine of pi n, think about that for a second. N is an integer, it's a non-negative integer, and sine of pi n is always 0. It turns out that if you look at this sequence, so the sine of pi n as n goes to infinity, I'm going to make this green. This happens to be just all the values where the function is 0. And so this sequence is really just the 0 sequence. It's a very boring sequence. It's just each time you plug in n, the term is 0. And so it's a constant sequence, and therefore it converges. And so the point here is that it's possible for the limit of a sequence to converge, but the limit of a function not to converge. Okay, so that's possible. On the other hand, if the function converges to L, then the sequence will as well. Okay, so if, I'm going to call this a theorem, if the limit of f of x as x approaches infinity is equal to L, then the limit as n goes to infinity of f of n, or if you like, if instead of thinking of this as a function, if you want to think of it as a sequence, the limit of a sub n as n goes to infinity, that must also be L. So if a function settles at the value L, then so does the sequence. And that makes a good amount of intuitive sense if you think about it. So if I were to take a graph here, I'm annoyed that my pen just cut out there, but if you take a graph, and now take a function who's eventually going to settle around the value L. So you have a function, and it's eventually going to settle around L. Well, what that means is that when x is arbitrarily large, all the values are close to L. And now if you take a sequence, what you're doing is you're taking a bunch of points that are kind of equally spaced out according to their x values. So maybe here, 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 and so on. And so all the values on of the sequence are also going to get arbitrarily close to L. Because what we just said, this is kind of a strong statement to say that a function approaches L. That means that all the values, okay, are going to be within epsilon units of L for whatever epsilon you want. And in particular, the integers are going to also have that property. Okay, so since this is true for all x values, it must also be true for the integers. And so that's the kind of basic theorem here. The reason why that's useful is that there is no L'Hopital's rule for sequences. And if I were to look at the limit of, say, sine of n over n, there is no L'Hopital's rule for sequences. You can't apply it. L'Hopital's rule only makes sense when you're talking about the limit of a function f over g. Okay, and the f over g thing, really you need, in order to talk about derivatives, which is what's necessary for L'Hopital's rule, you have to talk about continuous functions. You can't talk about derivatives at points. It turns out you more or less, this is generally fine. And I have the wrong example here. Yeah, I wanted to look at something like n squared plus 4 over 2n squared minus 3 as n goes to infinity. And so it turns out what's going to happen here is what you want to do is you want to look at the limit of the function. X squared plus 4 over 2x squared minus 3 as x goes to infinity. And so this will be infinity over infinity, and therefore you can apply L'Hopital's rule, and you get 2x over 4x as x goes to infinity. And then you can either blindly apply L'Hopital's rule again, or realize that you don't have to. 2x over 4x is just a half. And that's what happens to the function, and therefore that's what happens to the sequence. Okay? So technically you can apply L'Hopital's rule to sequences, just to functions. It turns out if you can apply L'Hopital's rule to functions, you can also do it to sequences, so it's kind of okay to do it to sequences, but I'm going to continue to do this to functions as well. And so, for example, if you were to look at the limit as n goes to infinity of, say, 1 plus 1 over n to the n, this is going to turn out to be e, and that's basically because we already know that the limit of 1 plus 1 over x to the x is e from our discussions in chapter 6. Right? We already know that that gets bigger and bigger and approaches e, and therefore the same must also be true for sequences. Okay? Now, the last thing I want to say here in regards to limits is what's called the monotone convergence theorem. In the monotone convergence theorem, I think I have this saved already. The monotone convergence theorem talks about, nope, I don't have it saved. So the monotone convergence theorem talks about the following. So the monotone convergence theorem says that if you have a sequence, I'm talking faster than I'm writing here. So if you have a sequence A sub n, and A sub n is monotone and bounded, then the sequence converges. Okay, and that's the monotone convergence sequence. And the idea here is, again, pretty clear. If it's monotone, what ends up happening is the function's always moving in one direction, or the sequence is always moving in one direction. And if it's bounded, that means that it's eventually going to kind of level off. It's never going to get above a certain value. So think about what it means for a sequence or a function even to diverge. Often what happens is that it's unbounded and goes to infinity. That can't happen if the sequence is bounded. And the other thing is something like sine of x, where it alternates, it kind of oscillates. And that can't happen if the function's monotone. Okay, so I'm not going to prove the monotone convergence theorem, but that's roughly the intuitive idea. Okay, and so that's the monotone convergence theorem. The last thing I want to mention, sorry, I know I promised that this monotone convergence theorem was the last, but the last thing is the squeeze theorem. The squeeze theorem is still true for sequences. So if the limit of a sub n and the limit of c sub n is equal to L, so if that's also the limit of c sub n as n goes to infinity, and if a sub n is less than or equal to b sub n is less than or equal to c sub n, then b sub n also must converge to L. Okay, basically same idea as before. This is also true for sequences. All right, that's enough for now.